Good morning. I'm sorry, I was having some issues with the system. Just decided to reboot. So I think we can start. I'll just make a brief introduction to our guest panelist today, and then she can start with the presentation. Okay. So we have with us today Dr. Kavita Deshpande, who recently joined us in the School of Computing and Data Science as an associate professor of mathematics and data science. Dr. Deshpande has 20 years of teaching experience and 10 years of research experience in mathematics, and has worked across the domain, including representation theory, numerical linear algebra, scientific computing, and computer vision. Dr. Deshpande earned her PhD in mathematics from Northeastern University, Boston in 2012. She has several publications like the phase counting formula for toric arrangements defined by root systems, deletion restriction toric arrangements, orbit closures of source sink link in quivers. So she began her career with Ferguson College as a lecturer in 2003, followed by working with Bhaskar Acharya Pratishthan, Pune. She then went on to be a teaching assistant and a PhD student in 2006 at Northeastern University, Boston. Subsequently, in 2012, she joined Chennai Mathematical Institute as a visiting fellow and further took responsibility as a lecturer up until recently. During her tenure at CMI, she has been the faculty advisor for the MSc Data Science program. She has also served on CMI's Grievance Committee and the DS Admissions Committee. At Sai University, Dr. Deshpande will be responsible for teaching and helping build the computing and data science program. So thank you for being with us, Dr. Deshpande. It's over to you now. Ma'am, you're on mute. I think you'll have to unmute.
Okay. Is that better?
Yes, yes.
Yeah, so I said thank you, Sanjeev, for that introduction. And thank you for this opportunity to talk with the students, something that I have been wanting to do for some time. The title of my talk is, Do You See Matrices Everywhere Yet? And this is, so I understand that there are some second year students in the audience, and some to be first year students in the audience. So I'm trying to ask this question actually to the second year students. So because they have seen some data analysis, hopefully in the last year. So I want to ask them, and even the new incoming students, if they do realize at some point that matrices are everywhere in their life. So let me start, since I'm talking. This allegory says that the matrix is everywhere. Although in the movie, the matrix is a sinister entity. But we are not going to deal with any kind of sinister matrices. Okay, so if you have seen matrices before, maybe in high school or in the first year of your study, have you thought about what they are and how they arise in real life? So it will be nice to have an interactive talk here. So, have students seen matrices before? Have some of you seen matrices?
For one.
Yes. Yes, they are. Hello?
I'm not sure what they're used to, but I just learned the method to do it. That's it.
Matrices are? Hello?
Numbers dependent boxes.
I'm not able to hear you clearly, but okay. So if you have seen them already, probably you've noticed that they are simply arrays of numbers, right? A matrix is nothing but an array of numbers. So you must have seen various kinds of matrices. Maybe you have seen square matrices where the number of rows is same as the number of columns. But there are also rectangular matrices where the number of rows may not be equal to the number of columns, and so on. Okay, but essentially they are arrays of numbers. Okay, so it is data arranged, but data not in terms. So you cannot have a railway timetable and call it a matrix, right? So railway timetable consists of the elements in that timetable, or the entries in that timetable are times, correct? So that cannot be a matrix, because that entry is not simply a number, but it actually means something else. Okay, similarly, you cannot give me a table consisting of words or sentences as the entries, that's not a matrix. A matrix is simply an array of numbers. Okay, so you should have numbers in there. And then where do they arise? Okay, why did they first arise? Why did people start getting interested in matrices? So historically, people started getting interested in this way of writing numbers because they provide a very convenient way of describing systems of equations. Okay, so this is probably something you have seen, right? You have seen, you've talked about systems of linear equations, maybe in school. So where you have seen, let's suppose you have two equations. Okay, so suppose I give you two variables x and y. Okay, and I ask you that what are values of x and y that will satisfy this equation as well as this equation. Okay, so the question is, are there x and y which satisfy both of this simultaneously? Correct. So this is what you saw in school as simultaneous equations, probably. Right, so simultaneous means you want values of x and y which satisfy both of them. Okay, and then this you know how to do. Correct, so you will eliminate one of these variables. So you suppose, so can you help me through this? How will I go about finding this values of x and y here?
Multiply the second equation by 2 and cancel the x.
That's right. So what? That's right. You can try and multiply this equation by 2 so that you get the same coefficient for x, and then you subtract, right? So that is going to lead you to 3 minus 17, so minus 11, y equals 5 minus 4, so that's going to be 1. Okay, and so you will have y equals minus 1 by 11, and then you substitute this value of y in any one of the equations, that will give you the value of x. Okay, so if you are dealing with only two variables and two equations, this is very simple to handle. Okay, so now suppose you are not dealing with just this. So suppose you are still interested in simultaneous solutions, but now you are dealing with three variables. Okay, you have three equations in three variables. Okay, so if you were really asked to solve this, okay, z equals 1, x plus y plus 2z equals 2, 3, so 3 is, okay, x plus 3y plus z equals 3. Okay, so I have three equations in three variables, and I ask you to solve these simultaneously. Okay, now you might still, try doing the previous, try using the previous idea where you are multiplying and getting rid of one variable. Okay, so what you have to do now is take two equations at a time and get rid of the same variable. Okay, so something like that. But people soon found that, okay, instead of looking at it like this, if you just write the matrix of the coefficients, so now what this does is, so I'm writing the coefficients of x, y, z as these columns. Okay, 1, 1, 2, 1, 3, 1. Okay, so instead of looking at this system of equations as these three equations, I can also look at it as trying to solve this matrix equation. Okay, and why does that make life simpler? It makes life simpler because now when you go or set about to solve this, you can deal only with this. Okay, so because now this is not 0, 0, 0, you will actually have to deal with, let me make this a simpler situation. Okay, yeah, so in this situation, you only have to deal with the matrix here, and you are not encumbered by this x, y, z all the time when you're working. Okay, and the whole process of solving this set of simultaneous equations can be streamlined, okay, very nicely, and that method is called row reduction. Probably this is also some of you must have seen before or seen in high school. Okay, so you can give a nice algorithm, nice stepwise method of row reducing this matrix, okay, and then solving for x, y, and z. Still, you might think, oh, it's only 3 equations in 3 variables. I might just do it by hand or not by using matrices. But the real problems occur when you're not dealing with just such small problems. Okay, if you're dealing with in real life the kind of systems of equations that you might need to solve consist not of 1, 2, or 3, but say you have 50 variables. Okay, so you have 50 equations in 50 variables. Okay, now would you do it by hand? Do work with 2 equations at a time, then 3 equations at a time, and then 4 equations at a time? That is simply not possible, right? So then this method really becomes the way to go. Up to x50 equals whatever this vector may be on the right hand side, okay, depending on the equations. So that is why solving a system of equations using matrices is much simpler, because now you are focusing only on this matrix and you can deal with that array of numbers irrespective of these variables. Okay, these are in the background. You don't have to keep on working with them each time. Okay, so that is one of the historical reasons why people started looking at matrices. Okay, and of course then people found many other uses for them also, but in the context of today, in the context of data science and data analysis, the aspect of matrices that concerns us most is this third one, that matrices actually provide a very convenient way of expressing data itself. Okay, so they provide, so as I said before, you can have a railway timetable in the form of a table, okay, or you can have other tables, but you can also express the day-to-day data that we use in terms of matrices. Okay, how is that? So here is an example. Okay, so here is something called a recommender. Okay, recommender. Something called a recommender system. Okay, so a matrix that might occur in a recommender system might look like follows. Okay, so everybody has heard of Netflix, right?
Yeah, yes, ma'am.
Yeah, so Netflix. So Netflix used to be very popular. Now the popularity has gone down a bit, but it used to be very popular. And it was one of the pioneers in this recommender system business. So what did Netflix do? It collected data of the kind of movies that users prefer. Okay, so it had users versus genres. Okay, so there is this matrix. So every user, when the user watches a movie, okay, so suppose you watch a movie, and then at the end of the movie, Netflix will ask you how you like the movie. Okay, you rate it between 0 to 5. Okay, so 0 stars to 5 stars. Okay, so you will give a rating for every movie that you watch. Okay, now Netflix will have these various genres here. Okay, so the movie could be a drama or I don't know, comedy, okay, or some kind of horror movie and so on. Okay, so these are the various genres, and then there is user 1, user 2, and so on. Okay, and the entries of this matrix will be exactly the rating that the user is providing to the movie that they have watched. Okay, so by the way, this need not be just genres. Okay, this could be actual movie names also. Okay, so slowly what happens is, as people keep on watching movies and offering their ratings, this matrix starts getting filled up. Okay, so maybe user 1 has watched a drama movie and given it 5 stars. Okay, and a comedy. So over time you find out that user 1 seems to like drama movies more, okay, and certain kinds of horror movies a little bit, but certain kind of comedy movies not at all. Okay, so over time this data keeps on increasing. Okay, So this data of ratings is expressed in form of this matrix. Okay, and the recommender systems actually do computations using this matrix to try and recommend to users based on their previous ratings. Okay, so if the matrix has found out, okay, or the program has found out using this rating matrix that a certain user prefers political dramas, okay, then the next time the user will be recommended political dramas. Okay, so you have these recommendations when you go to your Netflix page based on whatever you saw before. Okay, the same kind of thing happens on Amazon. Okay, if you have done Amazon shopping, okay, you have bought certain things, or even if you don't buy, suppose you click on a certain product, and then it will show you similar products. Okay, so that similar products is based on how similar the product looks to the product that you're choosing. There is also something called as users that bought this product also bought, right? You might have seen this on Amazon. Okay, so that kind of things, that kind of recommendation comes from a matrix like this, because you will be compared based on that product. You will be compared to other users who bought that product. Okay, and then because the other users bought these products, the system says you might also be interested in these products. Okay, so that is how recommendation works. But the point is that this is all based on this matrix of ratings that the users provide over time. Okay, similarly, Swiggy nowadays will also recommend. Okay, so many of these recommendation systems are based on this data collected from users. So the point that I want to make is that matrices provide a convenient way of expressing the data. Moreover, going ahead, not just you can store the data, but you can also do matrix operations to analyze that data. Okay, so because now you have a nice array where all the data is contained, you might think that, maybe this is too big and I'm not able to, maybe this is like a 10,000 by 5,000 matrix and I don't know how to analyze this, okay, or how to look at this data. But you can use matrix operations and linear algebra, okay, to reduce the dimension of that and still conserve the most important information that the matrix contains. Okay, so that is another thing. Not only are you expressing data, but you can also manipulate data, and you can draw inferences from that data. And this part of manipulating data, okay, this is where linear algebra plays a role. Now that your data is expressed in terms of matrices, you can use the power of linear algebra to manipulate that data, okay, to bring it to a nice form where you can go ahead and draw inferences from that data. Okay, so that is how data analysis works really, if you take a bird's eye view of this. Okay, so now let me show you two examples, okay, two very broad examples, one in the area of text analysis and one in the area of image analysis. Okay, so here is an example of what is called as information retrieval in text analysis. Okay, so text analysis is a more general term, but in that text analysis there is something called as information retrieval. So what does information retrieval mean? So suppose you are in a library, okay, and you are looking for some book title. Okay, how would you go ahead and look for that book title? So earlier on there were cards. Okay, I don't know if the kids of this age know the card system at all, but so earlier on there would be drawers full of cards, okay, arranged in a certain order. And so if you wanted to look for your book, you scan through those cards manually, okay, and found your book where it is placed. Then you actually physically go to the location and pick up the book. Okay, nowadays what you do is there is a library website where you go and you enter the book name, okay, or the author name, and then the location of the book is displayed, and then you go and pick up the book. Okay, but now suppose it is, so sometimes data can be more complicated than this, not just book titles in a library, but you can have websites. Okay, so for example, everybody is used to doing Google search, right? So you want to look for a website which contains certain information. Okay, so what kind of information? Hello, sorry, my there was a power cut. There was a power cut here. So let me just get back. Yeah. So, so the situation might be a bit more complicated. You're looking for a recipe for dal makhni. Okay. So suppose you are saying, but it's not that simple. You want to make dal makhni without onion and garlic today. Okay. So suppose you are looking dal makhni without onion and garlic. Okay. So now that is not like a book title or something very, that the entire document will be titled by that. Okay, so you want to look for all websites which contain this kind of information. Okay, and that information can be embedded within the website, need not be the title of the website. Okay, the title of the website could be I don't know, food forever or something. Okay, so that might be the website name, and this sentence or these words might be somewhere inside. Okay, so now you're not really looking for book titles, but you're looking for your query embedded within an article, right? So when this kind of information is required, so you have, of course, thousands and thousands of websites or web pages, and you're looking for this one piece of information, and you would like to, find the web pages which contain this information. Okay, so something like this, to retrieve these web pages, this kind of thing is called as information retrieval. Okay, you want to find documents that are most relevant to the query. Okay, so this area is called as information retrieval in general. Okay, so I'll give you a very small sort of baby example in information retrieval, and how that gives rise, how arranging that data really gives rise to a matrix, and how manipulating that matrix or the entries in the matrix gives you some actual information in the end. So one of the most commonly used models for the information retrieval task is called as this vector space model. Okay, in which each document is encoded as a vector. Okay, so how is this done? So here is a very small example. So what is done is that the data, the text, which means text can be the terms that you're interested in. Okay, so this could be terms of interest. Okay, so these are terms, and then there are, so you're looking for these terms of interest in these book titles. Okay, so suppose that is what you're doing. Okay, so I have these 5 terms here and 6 books, and I want to find the book title which contains the terms that are listed here. Okay, now this is a baby example, and you can do it by just looking at it. Okay, but in practice, of course, there are thousands and thousands of terms and millions and millions of documents that are processed. Okay, so how does this give rise to a matrix? So the term document matrix is sort of formed in this following way. So you have documents as columns. So you have document 1, document 2, 3, 4, 5, 6. So your 6 documents form the 6 columns, and your terms, okay, form the rows. So term 1, term 2, term 3, term 4, term 5. Okay, and the entry of the matrix Aij is the ijth entry, which means, so Aij is entry in ith row and jth column. So for example, let's look at T1. So what entry will come here? This entry represents whether the term T1 appears in the document D1. Okay, so here I have done a very simple binary representation, which means if the term occurs, I am putting 1. If the term does not occur, I'm putting 0. Okay, there are other representations also possible. Of course, there can be, if a term is repeated, you can have the number of times the term appears in the document. Okay, that's another very common representation. And there are a few more representations also that are in use. Okay, right now we are going with the most simple thing. We are doing a binary representation. If a term occurs in a document, then I'll put 1. If the term does not occur in the document, I'll put a 0. So the word cell or cells or cellular, okay, if any of these occur in the document DI, I will put 1 there. Okay, so now since none of the word does not occur in D1, okay, so I put a 0. Now here the word cell does appear, so I've put a 1 here. Okay, the word cell appears in D3, so I've got 1. The word cellular appears in D4, so I've got 1. The word cell, cellular, none of these appear here. Okay, so I've got a 0 here. And similarly, I've got 0 for D6. Okay, is this setting clear? How I'm getting the entries of this
Yeah.
matrix?
Yes, ma'am.
Yeah. So this is how, for every term, you can write the corresponding row, depending on whether that term appears in the matrix or not. Okay, so this is how this matrix appears in information retrieval. Okay, this is called as the term document matrix, and I will show you towards the end a small analysis of this. Okay, or how this can be used in to actually answer some query. Okay, another place where the other example that I want to show you where matrices occur is this area of image analysis. Okay, so image analysis, well, you must have seen you must have all seen digital images, right? You take selfies on your cell phone, you look at pictures all the time. Okay, so what is a digital image? Does anybody have sort of a nice description or a quick description of what a digital image is? How is a digital image formed? Any one of you having interest in physics? Images generated, yes, computers also do generate images. But what happens when you take an image, when you take a picture, when you take a selfie? What is the process? How is the image formed?
By rows and columns of pixels.
Yes, so that is how it is stored, right? That is how the image gets stored on your sensor or on your cell phone memory. Okay, so how is it formed? So you have your camera lens. Okay, you have your sensor here in your camera or in your yes, each small unit of the image is a pixel. That's right. So this sensor is divided, right? Each unit is called a pixel. This is how the sensor looks like. So the light comes in through your camera lens and it falls on the sensor. Now the sensor is coated with photosensitive material. Okay, and depending on the intensity of the light that's falling on this part, okay, there is also like joined to the sensor, there is a processor. Okay, so nowadays this is sensor plus processor. So what this processor does is, depending on the intensity of the light that falls on the sensor, say at this point, it will assign a number. Okay, so this sensor will give rise to this grid of numbers. Okay, so suppose let me just talk about black and white images for the moment. Okay, so that means if it's a black and white image, okay, then a black and white or a grayscale, okay, then the values will range from 0 to 255. Okay, so if the intensity is very high, but which means it's a white okay, very high intensity, then the number that goes here might be as big as this. Okay, and if here, for example, there is no light falling, then here the number that will go is 0. Okay, and intermediate values filled up everywhere, depending on the kind of light that is falling on each of these, square or these small pieces of the sensor. Okay, so this is how the digital image gets stored in form of a matrix. This is what a digital image is. Okay, and this matrix is to be analyzed to detect whatever all kinds of image analysis jobs. You want to detect the presence of objects in an image, or you want to recognize faces in an image. Okay, just like Facebook does, or maybe even your cell phone camera does these days. Okay, counting objects of interest. So in a given image, how many bottles are there in this image? Okay. Also interpreting the image. This is very state of the art. Interpreting the image means actually the machine will tell you what is in the image. Okay. So all these kind of things, image analysis can be done by analyzing this matrix. Okay. Because see, after all, what is an image? So for humans, this is what we will see. Okay, or this is what we write, or this is what is there in the real world. But when it falls on the sensor, okay, first thing you have to realize is there is no continuity. Okay, everything is discretized. It has to be put in these blocks, right? So when you divide this into blocks, then there will have to be some kind of code that says, okay, if you see this black piece here, okay, if you see this black piece here, then you color this entire square black. Okay, and if you see no black piece here, then you keep this entire square white. Okay, so this is called digitization. Okay, this process is digitization or discretization, any one of these. Discrete because these are now separated into pieces. Okay, so this is how it gets stored. Okay, and actually on the computer, when it is stored in terms of signals, it will be stored as this matrix. Right, so this is what a human sees, and this is what the computer sees. So the computer doesn't have any sense of what this earlier image was. Okay, so let me give you a more clearer. So here the human sees this image as an image of a cat. Okay, but for the computer it is stored just as this matrix. The machine has no way of knowing what is in the image. It only has these set of numbers. Okay, and it is these set of numbers or this matrix of numbers that the machine has to analyze to detect and tell whether the image was that of a cat or a dog. And that is why that is such a big achievement in computer vision, being able to tell between two objects. For a human, we sort of take for granted our cognition, what the human vision can do, how the human brain can process this information so quickly. Okay, so this is all something that we all take for granted. Okay, and it in itself, it's a very beautiful subject area, human vision, how the whole thing works. Okay, very complicated, very interesting, and very beautiful. And similarly, this on the technology side, this is also a very interesting problem. How do you make a computer do what the human vision does? Okay, so computer vision is extremely this extremely exciting area where you're trying to analyze and then sort of copy in codes what the human vision is actually achieving. Okay, so now these are the two examples. These are two examples in which matrices have arisen from text data and from image data. Okay, so now what I want to talk about is what do you do with this matrix? What next? So in 2 minutes, I will talk about the text, and in another 5 minutes, I will show you what you do with the image. Okay, so one example of each. So with the text data, as I said, that you can meaningfully manipulate the data and you can draw insights from this. Okay, for that you use tools from linear algebra and numerical or matrix computations. Okay, so using these tools, you can manipulate and draw insights from data. So for example, going back to our text analysis example, where you had the term document matrix. Okay. Now, suppose you want to handle a query, which means, like that question you had, how to cook dal makhni without onion and garlic. That's your query. Okay. So you form the query vector, just like you have formed vector for the documents. Similarly, you form a vector for the query. Okay. So the terms that will be in your query will be dal, makhni, onion, garlic, and because without is important for you, you will say without. Okay. These are terms that you want to see in the documents that are given to you, right? So you form the query vector. Okay. And then you use notions of what is called as vector similarity. There are many ways in which you can say two vectors are close to each other. Okay. One of those is cosine similarity. Cosine similarity means you actually find the cosine of the angle between the two vectors. Okay. So if the cosine, is of angle between the two vectors is computed, then based on that you can decide whether the document is close to your query vector or not close to your query vector. Okay. So you can use notions of vector similarity to decide this. Okay. Now, what I'm telling you are very sort of, basic or, as I said, baby examples. In practice, more sophisticated versions of this idea are used. So you could probably see more of these in the, courses that you might see in your later years at SAI. Another thing is that in practice, the dimensionality is reduced. Okay, so in practice, if you're dealing with, say, a 10,000 by 15,000 matrix, okay, then it's not these very basic ideas that are applied, but one first reduces the dimension of that matrix and then tries to draw conclusions. Okay, so in practice, one does these two things, but right now I'm not going to talk much about these. I'm just going to show you a simple that earlier example in this simple form. Okay, so coming back to this. Okay, so we had this text document matrix that we saw earlier. Okay, and now suppose we have a query. Okay, so our query is we are looking for the book or document named Human Biology. Okay, so with respect to these terms, our vector, so the term cell or cellular doesn't appear, so we will have a 0 for the query vector here. This term doesn't appear, this term doesn't appear, but in human biology, biology is appearing, and this term doesn't appear. So this is going to be our query vector for the term human biology. Okay, so that's what I have written here. So this is the query vector. Okay, so this you find the cosine similarity between this vector and the other document vectors. Okay, so 1, 2, 3, 4, 5, 6. These are the 6 document vectors corresponding to these 6 documents. Okay, so you find the similarity between the query vector and the first one, query vector and the second one, query vector and the third one, and so on. Okay, so you compute this. There is a formula that uses the standard formula for computing the cosine between two vectors. Okay, so you compute this for every document and choose the document which gives the largest similarity value. Okay, so in this case, if you see, well, the first document has all zeros, and so you can guess that I mean, if you have seen this formula before in high school, you can easily guess that the first result is going to be 0. Okay? And so on. Well, I'm not going to go into solving this one for you, but the point is that you get these values, okay, that describe the similarity values between the query vector and those 6 documents. Okay, and you pick up the largest of this. Okay, so what will be the largest one here? So I have these 6 numbers, 1, 2, 3, 4, 5, 6. So of this, I'm going to get the largest one to be
Cos theta 3.
cos theta 3, right? Is that going to be the largest entry?
Yes, ma'am.
So then which is the document that corresponds to that entry?
Third column. Oh, the document is, I think, D3.
D3, right? So D3 corresponds to theta 3, okay, which has the largest similarity value. And so the program that you write using this cosine similarity is going to throw up this document to be closest to your query of human biology. Okay, and so you will be led to reading essential cell biology. If you have only these many documents, okay, but in practice, of course, there are thousands of book titles and other information also. So the results are much better than you see in this baby example. Okay. So moving on, let me quickly show you this in the image analysis part. What is the kind of matrix or how matrix analysis or matrix manipulations give you some results. Okay. So I have a nice demo for you here. But let me quickly run you through what is called as the singular value decomposition. Okay, so singular value decomposition is a matrix factorization. So you know what is a factorization, right? So for example, integer factorization, correct? So 24, how do you factorize 24? You could factorize it as 2 times 12. Or if you want a complete factorization, then this is going to be 2 times 2 times 2 times 3. Right? So this is a complete factorization, but this is also a factorization, or this is also a factorization. Okay, so there are many different factorizations that you may write for an integer. Similarly, there are ways of factorizing matrices. Okay, so there is something called as matrix factorization. There are many different factorization. What you do is you are given some matrix A, you try to write it down as the product of two matrices, sometimes 2, sometimes 3, okay, matrices B and C. So that when you do matrix multiplication of B and C, you get back A. Okay, so that is the idea of matrix factorization. Now the SVD or the singular value decomposition is a particular matrix factorization. It is a factorization into 3 matrices. Okay, this is a matrix U, this is the matrix sigma, this is the matrix V, actually transpose of V. Okay, so what this is doing is it is breaking up A into a product of 3 matrices. So that if you multiply out these 3, you will get back A. That is what it means to have a factorization. Okay, and the singular value decomposition is an extremely useful factorization of a matrix. Okay, and it is used extensively in data analysis tasks. Okay, so this will be one of the most important factorizations that you will see in your linear algebra class. Okay. Okay, so the point is that how does this help? So this helps in many different image analysis tasks, and one of the tasks that I want to sort of show you the demo of is image compression. Okay, and so the way image compression works is, so suppose your original, so instead of sentences and terms now, okay, so suppose this is your image matrix. Okay, so this is some digital image like what I had shown you earlier. Okay, you take that matrix and you take its singular value decomposition. Okay, now after one takes the singular value decomposition, sort of you can decide how much you want to. So you have broken up A as a product of 3 matrices, right? Now in compression, what you want to do is you don't want to store this entire data. You want to probably store lesser amount of data, but have almost similar information that you had before. Okay, that is the idea of data compression. Okay, you want to store it in smaller space, but you don't want to lose too much information. Okay, so when you want to do something like that, one of the ways of doing it is, you take this factorization and you, instead of taking the whole U, you take part of U. Okay, so that is this gray shaded part here. Okay, you take a part of U. So suppose you have taken first K columns. Okay, then you look at the corresponding K by K submatrix here and K rows here. So if you take a product of these gray parts, okay, then that is going to give you an approximation of A. Okay, so this is the product of just the gray parts. Remember, the original A is actually U sigma V transpose. Now what you're doing is you're taking a part of U, a part of sigma, and a part of V. Let me call that part U prime, sigma prime, V prime. You've taken small parts. This is going to give you approximation of A. Not exactly A, because definitely you're losing some part, right? You're losing this data on this side, this, you're losing, okay? So you lose that, but you get a very good approximation of A. The best you can get is given by the singular value decomposition. And this approximation A prime is what you store, okay? Now this is going to require lesser space than the original because you have lost some data. You have chosen to lose some data, okay? So this is going to take up lesser space, but the singular value decomposition makes sure that you have lost data that is not too relevant to the information provided in the image. Okay, so that is the beauty of SVD. Okay, the SVD takes care that the most important information is retained and only that which is not so important is lost. Okay, and so this is how data compression works in general, and image compression will also work if you apply this to an image. Okay, so let me now show you a nice demo of this. Okay, so I'm going to move to okay, so yeah, so you see this, right?
Yeah, yes.
Okay. So now in this, let's look at, so this is the original image. Okay. And now what is being done is data compression or image compression using SVD is being done. Okay. So what does it say? So the scale here, the slider scale that you see below here, okay, is going to decide how many, what that K is, okay, how many columns or how many pieces of information you are going to keep. Okay, so if I take this slider to 0, then I'm saying that I'm not going to keep anything. Okay, so I should actually see blank, but they are not showing me. Oh no, the lowest is 1. So this is saying that I want to keep 1 column of U, okay, and 1 entry of sigma and 1 row of V. Okay, then the image, this original image, the only thing I'll retain is this blur. Okay, but now look, the original image size is 600 by 402, okay, which translates to these many pixels, okay, 2,41,200 pixels. This is the original image size, okay, and what we want to do is compress this. So now what we can see is that, suppose I take, okay, choosing 1 column doesn't tell me anything about the image, okay, so let me take 2 columns. So I see some details appear. 3 columns and so on. Okay. So as I increase the number of columns, I start getting more and more information. Okay. Of course, if I take the slider whole way here, okay, if I take it, not the whole, so sorry, I shouldn't take it there. I should take it to how many? If I take it, say here, this is almost like taking the whole image. See, look at this this size. This is almost same as the original. Okay. And so the image is going to be almost like the original. Okay. So if you keep if you take these many rows and columns, then you are as well storing the entire data. You're not doing any compression. Okay. So what we want to do is we want to go down this scale, but not lose too much data. So you can see that if I go down this scale even up to 100, this doesn't look very different from the original image. Okay, if I take this down to here, okay, that number is 60. See, I can still make out what this image was about, right? Maybe not as clear as all the details are not as clear. It is slightly blurred, but I can still make out that this image contains mountains and trees and a lake. But now I have stored the image in 60,000 pixels. Whereas the original one was stored in these many pixels. Okay, so the compressed size is this much, and I haven't really lost too much in terms of image data. I can still make it out. Okay, maybe if I can go even lower. So this is too bad, right? So maybe, I don't know, depending on your preference, this is 50. So this is like 50,000 pixels. The same image being stored in 50,000 pixels. Okay, and you can still make out what this image was about. Okay, so and so on. You can of course have your all, or you can reduce the size. So look at this. Look at this number as I slide over the scale. So more rows and columns, then it's increasing. If I reduce, the number of pixels is decreasing. Okay, and we just have to strike a balance between, you know, the number of pixels and the image quality. Okay, so for most purposes, okay, if you are not doing some detailed image analysis and so on, this kind of image quality is fine. You don't need to. So 60,000 pixels looks like sufficient. Okay, if you want to just display this image, and you are not really interested in sub-pixel accuracy, this is good enough, right? So you can also look at other images. So I'll share this link with you. Okay. And so you can see this is computing the SVD. This is what is being done here. Okay, the SVD is being computed, and then so this is the original image, which has 44 lakh pixels. Okay, those many. But here I can do with much lesser actually, because there isn't too much detail in this image, right? If I go up to only 20, so look at how many, just 25,000 pixels. So this image size can be reduced to just 25,000 pixels, and I can still understand what's in that image, right? So compared to the earlier image where there was a lot of small, tiny details, this doesn't have tiny details. So this can be stored even in lesser space. Okay. So this is how image compression works. Okay. So this is what I wanted to show you as a demo. Okay, so that is the end of my talk. I could I can take questions now. If you have got interested in this, you can ask me questions. Thank you all for listening. There are some questions in the so some things in the chat. Yeah, so that's how computers store images with reduced file size. Yeah, this is one way. Okay, using SVD, image compression using SVD. There are many other ways also. Other algorithms are also there. This is one very simple way of reducing file size. Especially on your cell phones, for example. Okay, because your cell phone is small, the RAM will have to be small, and then you want to store thousands and thousands of images. They will always be in compressed form, not in the raw form. Raw means the whole original size. Does anyone have questions? Hello, am I audible?
Yeah, ma'am.
Oh, okay.
Ma'am, I have a doubt.
Yeah.
Yeah, like if you're storing it in a less amount of pixels, like in a phone,
Yeah.
if you take the image to a laptop, the screen is bigger now. So, like,
Sorry?
does it like no, like you're storing it in a lower amount of pixels, like if you're storing an image in a lower amount of pixels in a phone,
Yes.
then you're just sharing that image to a laptop. Okay, then now the screen is bigger. Okay, the amount of pixels the laptop can accommodate is more right now,
Yeah.
according to the screen. So now the quality will be less than if we see in phone.
Yeah.
Okay, thank you. I just need to clarify.
So yeah, so the quality is, yeah, see, the thing is, when you zoom in or zoom out, or you know, display from one device to another with different resolutions and all, the way the pixels in between the gaps get filled is interpolation. Okay,
Okay.
there's something called as interpolation, and that fills up the gaps. Okay, so if you're zooming out, okay, what happens is there will be some empty spots that need to be filled. Okay, so we can see this more in some image analysis class, where interpolation is the keyword there. Yeah.
Okay.
Taking images from one device to another. I can share this link with you and you can play around with this. See, it's computing the SVD.
Ma'am, I have what about the 3D images? It's 2D,
3D
like you're
image.
saying. Yeah.
What do you mean by 3D image?
Like not like 3D image. Like where they use an animated pixel to show you 3D now. Like
Oh, that I don't know much about 3D graphics you're talking about.
oh, okay, fine. Yeah,
You're talking about graphics, right?
Yeah,
Yeah, so graphics is also a lot of computer vision. Okay, but yeah, animation is like a completely different area, and 3D animation again is very complicated. But yeah, so what about that? What was your question about that?
No, like those images also are stored, right? Like if you're
Yes.
seeing an animated movie,
Yeah.
they're also stored, right? So like
Yeah,
is there
yeah.
any difference between them or
yeah, so
like,
again, compression is compression is used in all these. So it's not SVD that may be used. There are more SVD is a very how do I say, basic, very simple algorithm. Okay, which I described to you like in 5 minutes. I could describe what SVD does, right? But there are more sophisticated algorithms which you know do better jobs, or do jobs for higher dimensional you know data. So there are many algorithms, all based on linear algebra and these matrix algorithms.
Okay. Thank you.
So I hope you got interested a little bit into what linear algebra is about. Okay. And you know, I hope you got a small introduction into what matrices are about. And I hope also you got to see that, you know, matrices are really everywhere. Okay, whatever you do. So for example, you do a bank transaction, that gets stored as data in some matrix somewhere. Okay, so everything that you do in your daily lives using digital devices gets stored as data somewhere. Okay, and even if you are not actually doing anything on the internet, suppose you are just using your cell phone to take an image, even that is stored as a matrix. Okay, if you review something, that is stored as a matrix. Yes.
Yeah, I have another doubt. Like, is that only matrix the only method the data stored, or like is there any other method the data is stored?
I mean, if you want to do this kind of analysis and computations, then yeah, matrix data is stored as matrices, not necessarily a two-dimensional matrix, but could be a, you know, multi-dimensional matrix, like an array of matrices.
Okay.
Okay, so but yeah, the reason is that because for computers, this is a very readable data structure.
Okay.
Okay. It is also very convenient to work with matrices when you want to write algorithms and so on. Okay, so it's a very nice way of arranging data. More questions?
No, ma'am.
I hope I didn't put most of the audience to sleep.
No, it was interesting. It was pretty interesting, actually.
So, when we have the linear algebra class, we can actually do a small NumPy code for this kind of compression. You can see for yourself how this is done.
Ma'am, I have a question.
Yes, Abhishek.
I wanted to know when we'll be covering this topic in university, like during the first year or in the second year.
So linear algebra is being offered in the second year.
Okay, thank you.
So in the fourth semester, you will see linear algebra, and image analysis and text analysis we will offer that as a course in your third year.
Okay, got it. Thank you, ma'am.
So you are a second year student, or are you going to be a first year student?
First year, ma'am. First year.
Okay. So is Sanjeev here? Sanjeev?
I think he's kind of struggling with some network issues. He had messaged in the group that.
Oh, so this is now just all of us, is it?
Yeah, yes, ma'am.
Oh, okay, nice. So yeah, so in that case, yeah, if you have questions or you want to chat, you can ask me, okay? Or we can say bye and then we can meet again when the semester begins. So how many of you are first year students here?
I guess everyone knows.
Everyone? No, I mean going into the second year.
Oh,
Well, I'm second year student. Me and I guess Abhinav.
Okay, two of
Yes,
you are
ma'am.
second year students. I see. So all of you are CDS?
Yeah, two
Computing
of
and
us
data
are
science.
from CDS.
Yeah. Yes, ma'am.
Okay. All right. Yeah, it will be nice to see you all on campus and see you in class.
thank you, ma'am.
Thank you, ma'am.
Okay. Yeah. Okay. So if you have any questions, a quick question, you can ask me, or we can end this meeting.
If there are no further questions, then let's call it a wrap. Thank you so much for
Thank you,
presenting
Sanjeev.
today.
Yeah. Thank you.
Thank you, sir.
And thank you to all the students for being a nice audience.